Well, hello and good morning, and thank you for joining me here in my shop. Today is April 6th already. Looks like spring is starting outside finally. Snow is gone. Not coming back, I'm pretty sure at this point. So what I'm going to do today with this record player is I'm going to change the 6 capacitors. You can see the 6 yellow paper capacitors with new ones. Going to install a couple of electrolytic filter capacitors in the amplifier there to replace the power supply filter capacitor because the unit is humming, and I'm going to do the basic relubrication type maintenance on the record player and maybe investigate a little bit about why it's so noisy, but I'm not sure there's anything at all I can do about that. That's what I plan to do today, so I'm going to start off with the power supply electrolytic filter capacitors. So I have hunted for a schematic for this record player amplifier. I could not find one. So I'll have to just kind of play this by ear. This is the filter capacitor terminals here down here. There's 3 of them. You can see a couple of wires coming to it that are red and one that is kind of a yellowy color. So we can guess, we don't have to guess, this is a 3-part capacitor here, and we know 2 of them are 40 microfarads and 1 is 20. We can guess the 2 40s are part of the power supply, and the 20 is a bypass capacitor on what must be a single cathode resistor for the 2 output tubes, which are over here. This is probably the cathode resistor, but I don't know for sure. And this is probably a resistor involved with the power supply, but I don't know for sure just yet. So that's what we want to investigate, just to get comfortable with this. The most important thing is looking at how the shell, the metal shell of the capacitor, which you can see here. Here comes my assistant. A dying cat. Are you stuck? I looked at him. He's very sharply voiced this morning. The issue here is, if I'm going to replace the capacitors, I have to be careful about where I'm attaching the negative side of the filter capacitors I'm going to put in. Should it go to this metal chassis? Just hang on a second there, Peanut. Just hold on. Just hold on. He really wants to go outside because the sun is shining. And so by looking at the existing capacitor, you can kind of figure that out. First, there's a brown plate that okay, you know what? I have to go deal with him. That's it. That's it. I got 2 minutes. You gave me 2 minutes. Oh my gosh. I gotta go, man. Okay, both my cats are outside now in the sunshine. So I was talking about looking at how the grounding is done on the capacitor. And you can see a black wire there, and it's connected to the shell, if you like, the outside of this capacitor. Well, the whole capacitor is mounted on a brown insulated piece of material here to make sure that the outside of the capacitor does not contact the metal chassis. So now it raises another question in the same realm. So what about the chassis? What have they done with this? How is it connected into the amp, if it is at all? So all the electronics in here could just be floating in a metal box and not connected to it, but that would not be normal or common. Usually, somehow the metal box is connected to the amplifier in a way that will reduce problems with hum and things like that. So it's often done through a capacitor. So what I'm doing here is I'm looking very carefully to try to spot somewhere where something is connected right to the chassis. And I think I see it. So this is a little tricky to see. This capacitor's lead on this end of the capacitor behind this resistor, but you can't really see it. You can, but you wouldn't know you're looking at it. If you look right down through this area here, you can see a wire coming over to a terminal on this terminal strip. That particular terminal is riveted to this chassis. I'm willing to bet that that's the only connection to the chassis in this thing, through this capacitor. So the objective, and so where does the other end go? So the other end of this capacitor is probably connected essentially to the same place this wire is connected. There's probably a not so visible, continuous, not so continuous, electrically continuous wire running through here, connecting various things together, acting as the negative side of things, the return side, the grounded side, whatever term you want to use. And it would look to me like they've gone ahead and used the same kind of blackish wire here for that circuit. Now that would be typical, or a good idea. So I can see there's a black wire coming here. We follow and they all go around the corner here, and they attach together. Well, is that another grounded terminal there? Right here. So I'm looking at this terminal strip. How is that strip mounted in there? That's a really good question. How is it mounted in there? It looks like it's mounted from this terminal. It's pretty solid. I actually cannot see exactly how they've done it, but these are important things to figure out. Now, if you notice, there's a piece of cardboard here, right on the bottom. A square piece of paper or cardboard. Why would they do that? Well, it's to make sure something doesn't touch the chassis. It's insulation, preventing something from touching the chassis. And what would that be? Need a little more light on this to see. What it looks like to me is this terminal is under the rivet on that tube socket. So see, there's a rivet there. There's a rivet just beyond my finger there. There's another one over here, and another one there. Now the socket has to be held to the held in somehow. Okay, so you can see the rivet top there, and the other rivet here. It's just two rivets. That's how all the tube sockets are in. I have my finger on that rivet. Okay, so that rivet, I'm not sure. That rivet is the same one that I see here. It would appear that this is riveted to the chassis. This wire, this brown one. And what's that brown one? Let's follow that brown one. It's not one of the black ones. Doesn't sit here very good. There we go. So it's this brown wire. The brown wire is headed over to this other little chassis. It's coming in. You can see something kind of similar here. Some cardboard here. Terminal strip. And too many brown wires to see clearly what's up. Here's my flashlight, which I was looking for. Okay, so there's a brown wire coming in. Brown wire attaches to this terminal. That terminal is riveted to this piece of metal. And then it also, a brown wire comes off that terminal, comes up and connects here to this terminal. That terminal connects to this wire here. The other wire is a shielded wire, almost certainly carrying the actual audio signal onto these other two terminals. So to get it straight, the chassis back here, the main chassis, is connected with a brown wire to the chassis of this, and then there's a wire heading up, this wire, onto the record player. You want to take a guess where that's going? It's probably going to connect. I don't want to lose the needle here. Probably going to connect. Okay, this might be a little ugly. A little bit. Okay, so which one is it now? It's this wire. It's this wire. Oops. Up here, they are tied. They're taped together, so and they look identical. Well, not quite identical. But we can see the shield coming here, and what will be the signal wire coming here, I would think. And the other wire is connected to the bottom of the record player here, to this big metal piece. So what we've discovered is there is a wire connecting together the three chassis, if we can call it that. We can call this one of the chassis. It's not quite the right word. The little volume and trouble control chassis. Oh, that was bad. There we go. What was bad was I got this arm caught up against the thing there, but because the needle's not in there, saved. Okay, that's not very stable, but good enough. Okay. So we have all these chassis connected together. And then the chassis itself is connected via this capacitor. This one here. There's also a piece of cardboard underneath this terminal strip, so every terminal strip has a little bit of cardboard under it. The other side of this capacitor is connected to by a black wire back to this point, back to this negative on the capacitor. So essentially you have a whole electronic circuit here with one connection coming out of it to the chassis through this capacitor. Okay, nothing surprising in that. That makes perfect sense to me. The idea is if there's any signals being picked up, everything's an antenna, right? Everything is an antenna. So if you just left this box floating, there's kind of two problems that are going to come. One is it's going to pick up hums. From where? From all this stuff in here. And those hums are going to be conveyed around, and they're going to get back into the circuit, into the sensitive parts of the circuit, maybe where the first preamp tube is, and you're going to hear it coming out of the speaker. So in order to stop that, you basically short the chassis to the negative side of the power supply in here, but do it through a capacitor. Why is that? Let's look at how the power is handled in here. So where is the power cord? So here's the power cord right in front of me. It's attaching here. Two wires are heading off to run the motor in the record player. And some other wires are heading off, heading for this tube. This is the rectifier tube. Now, is there no transformer? There is a transformer here. Now, this may be for the speakers. As there's no other transformer. The speakers themselves. Let me just double check here. I have no transformer. So there needs to be a transformer to connect the output tubes to the speaker. It's an impedance matching thing that goes on. Speakers are very low impedance. Two plate circuits are relatively high in comparison. They use a transformer to do the impedance matching, or to turn some of the voltage pressure in the output of the output tubes into current to drive the magnetics in the speaker. So what can happen here is one side of the power ends up being connected to the negative terminal, if you like, or the negative side, or the grounded side, I hate that term, of the amplifier, straight there. So that would mean if you didn't have this capacitor here, if you had just a wire going from the negative bus, which is what we should call it, the negative side of the amplifier, if you had just a wire just attaching to the chassis, well, you'd succeed in draining all the signals and noise out of it, and you would solve that problem, or avoid that problem. But you would have a new problem, and that is, if somebody touched this, there's a chance it's not much different than sticking their finger into an outlet. You stick your finger into one of the two slots, you have a 50-50 chance of sticking it into the hot one. If we look at the plug, so this is before the system of polarized plugs in North America was introduced. So those plug prongs are the same size, and you can plug this in this way or you can plug it in that way. One of these two prongs is connected to them, well, they're both connected to these wires. When you plug it in, there's a 50-50 chance that this wire will be a hot one. 50-50 chance it's this wire that's the hot one. So because one of these wires is connected right to the negative side of the amplifier, connecting a wire from there to the chassis would essentially be plugging you into the wall. Now this is all inside the radio, or inside the record player, out of reach. But one thing that is certainly not out of reach is all this. In fact, you're going to be putting records on, you're going to be grabbing this thing over here. Danger, danger, danger. So no solid wire, instead a capacitor. A capacitor big enough to drain out the signals and get rid of the hum, but not so big that it'll let a huge current through that'll pass through your body because you've touched this, and maybe you have your bare foot on the ground. Maybe maybe you're playing these out in your backyard or something. Or you can be grounded in any one of a number of ways, touching a faucet, or who knows, a long list of different ways you can be grounded. And touch this, current will flow through you, through this capacitor. If this was big enough, you might feel it. There's a good chance you would feel it. Sometimes they call them brush shocks because you tend to be putting, like just brushing your hand along something, and you feel it a little bit funny. It doesn't feel quite right. If you're doing this kind of work, you know exactly what I'm talking about. You've experienced this quite a number of times. I'm pretty sure of that. So the amount of current involved is not enough to stop your heart or throw it into fibrillation, but it's enough to make you jerk your hand away, potentially, or certainly become aware that something's going on. If this capacitor is shorted, the whole thing becomes dangerous. But this plug on here, dangerous. Putting a polarized plug on here, even if you're careful, not a particularly good solution, because the situation depends upon whether the unit is turned on or off. It sounds a little crazy, but plug it in one way, I don't want to put it that way, wire it one way. When you turn it off, danger. Wire it the other way. When you turn it on, danger. Either way, there's danger. So not the easiest thing in the world to overcome this kind of thing. So what I do, I know other repair guys do different things. What I do is I just make sure this capacitor is good. So that one's a target for replacement for sure. So the reason I'm going through all this is because I'm trying to make myself aware of the situation with this, so I don't do something stupid and send back a record player to somebody who's going to get a shock off of it. I don't want that to happen, that's for sure. Well, I can see this is a 0.05 capacitor. I can see the number written on it. So okay, so I've gathered enough information now. I know how they've done the grounding to the chassis. There are radios and amplifiers where this capacitor is a solid piece of wire. There's usually a resistor in parallel with this capacitor too, usually like a 250,000 ohm resistor. If we look long enough, we'd probably find it. This might be it right here. This one is looks like a 30,000 ohm resistor right here. It's a little low, but there may not be a resistor associated with it. So that's the safety side of these things. I think that, the tip off right away is realizing that it's got an unpolarized plug and how old this is. This is from the 1940s. So here in North America, everything was built similar to this. You may have heard of the 5-tube radio and the hot chassis problem. That's exactly what we're talking about here. It's just not a radio. So I would call this a semi-hot chassis, not a fully hot chassis. If this were a wire, fully hot. Well, and why would they do that? Why would they put a wire here instead of a capacitor? Well, in an attempt to save money, they'll use the chassis as a wire, as a connector. The chassis goes everywhere, so it's available everywhere. And instead of having an extra black wire running around here and there, they can do away with the wire, save 2.5 cents, and just solder things right down to the chassis. So it's a cost-saving move. I guess, a couple of inches of wire and 1,000 of these adds up to something. Okay, well, I've talked a ton. Now, getting down to actually doing these. So the two with the red wires are going to be the high voltage. Now, we didn't find a transformer in this, did we? Didn't really settle that. This transformer is most certainly the output transformer for the speakers, the 3 speakers. There is no transformer in here for the power supply. So what they're doing is they're taking just the power, the voltage that's available in your outlet, 120 volts, and using that to develop B plus voltage, probably around 140, because the actual voltage in your outlet is stated to be 120. It has the same heating effect as 120 volts DC would have. But in fact, the voltage in your outlet is much higher because it's a wave. It's got high points, 0, and another high point. This isn't a low point, it's another high point. Reverse high point. Those high points are just under 170 volts. 170 volts. So if you rectify the 120 volts, you can come out with, well, I guess under ideal circumstances, 169 volts. Not like magic. 120 volts AC turned into 169 volts DC. Now you can't usually get all the voltage. There's voltage drop in the actual rectifier tube, some resistors involved. So typically you end up with a high voltage of around 140, maybe 150, maybe 130 volts DC. And that's it for this guy. So the tubes that are in here are operating with a plate voltage around, I would guess, 130 volts or so. So it's all adding up to be exactly what it is. So now the unit was humming, so the assumption is this capacitor is worn out. Pretty good assumption. We don't have to test it directly. What I need to do is install replacement capacitors. They're individual ones now, and much smaller, physically smaller. I know where to ground them. I need to ground them to this wire, or where this wire is going, or anywhere else that this wire ends up being connected to. The most convenient thing is, I think, to use that wire right there. Now I got to disconnect these terminals. You could choose to leave the old capacitor in and just put new ones in parallel, and you can get away with that. But I did have a radio I did just a week ago, and this type of capacitor was heating right up. I've never had one that heated right up, like really heating up. Well, in the long run, that's what will happen to this one too. The long run could be a long, long time from now. But maybe not. I didn't really check it. Maybe it's already getting hot. So the trick in doing this part is, how do you support the new capacitors, because these terminals you can't use. And I don't think it's too tough a call in here at all. I think it's It's going to be pretty easy to do. Put in 3 capacitors, 2 larger ones where these red ones are, a smaller one where the white wire is, all connected to this wire, and everything disconnected from here. One red wire goes to this terminal, the other red wire goes to this terminal, and in between those terminals is this resistor. So this resistor is the power supply filter resistor. Assuming that's orange, black, orange, be 30K, 30,000 ohms. That's exceedingly large. So this is probably not orange, it's probably brown. If this were brown, then this would be this would be a 100 ohm resistor. Why don't we just measure that? It looks to be in great shape. You really have no reason to doubt it. So let's do that. Oh gosh, I talk an awful lot. But I think it's helpful if you're new to this. This is all maybe of great interest to you. It should be. It should be of great interest to you. If you're watching this video and you've got a record player similar in front of you and you're thinking, I'll just do what Jim does. Be very careful. Sometimes I'm not explaining things, and also sometimes I'm explaining things wrong. So I don't think I'm too wrong about this. All the things I've said today. Okay, so across the resistor, in my experience, resistors tend to go high over time. They start out at whatever they're supposed to be and they just go up. The harder they work, the hotter they run, the shorter they last. So there you are, 107 ohms. That's just fine. That's no problem at all. Got the ohm meter out. Let's check these other big ones. Big resistors. So this looks like green. Is that green again? Black. So that's an unusual size. Well, we don't have to worry too much about this band. So green is 5. 5 something is probably blue. It's probably 6. 56 with no 0. So 56 ohms. 53 on the meter. Okay. And now this one also 22, red and black. So it's 22. This one would be what would this be? So this would be 22. So it's slightly up. You might as well check this one too. This guy looks like gray-red. What's gray? Gray is 8? I don't know. What's gray? And black. So again, it's another very low resistance. 88. So gray-red. It's supposed to be 82, but it's 88. So they're all a little bit up, but not enough to be concerned about at all. Very good. And now, do we dare waste our time trying to read the resistance across this capacitor? Well, we'll do it for fun, but this is not a reliable way to test a capacitor like this at all. I mean, it is really not a good idea. So it's doing a little bit of funny things, but it's up in the mega ohms across here. I think it's my reading a very high resistance and not making very good contacts to do it. So that's not a valid test anyway. The test will come when I remove it and actually test it. Okay, so what I'm going to do is I'm going to install the 3 capacitors in here, the 3 filter capacitors, 2 filter capacitors and 1 bypass capacitor. So let's talk a little bit about the bypass capacitor, because that leads somewhere too. So one of these resistors is going to be the cathode resistor. Almost certainly it's this one. The cathode resistor's purpose is to raise the voltage of the cathode a few volts so it goes positive relative to the grid, and the grid stays close to ground potential, if I can use that term, close to 0, if I can use that term. So that's a way of biasing the two. So you can either drive the grid negative, which is tricky. Where's the negative voltage come from? Or you allow the cathode to rise up by sticking a resistor in the cathode circuit. The difficulty with that is now the signal you're trying to develop and send out to the speakers is working inside this resistor, in the cathode current flowing in this resistor. And the result is some of the power is spent in this resistor. Well, that's kind of a waste. You want the power in the speakers, not in this resistor. So a trick that can be used is to short out this resistor with a capacitor. It's only shorted in terms of the signal. In terms of the DC voltage, it's not shorted. So you put a fairly large capacitor across this resistor, and you essentially ground the cathode, and that allows all the power that the tube is developing, the signal power, to be delivered to the speaker, or at least go in that direction. You can stop the wasting here. Typically this is around 20 microfarads to bypass this. It's called a bypass capacitor. And there it is, 20. Excuse me. So we've already tested this resistor and found it more or less matched its coding. And a little bit of variation is not important. All these things are plus and minus 10% anyway. Excuse me. Maybe the last thing of interest before we get right into this is what about this unusual guy here? So it says electro ohm, 600 ohm. This is a resistor inside of a protective case, and the case looks like it's porcelain. It's a material that can withstand a lot of heat. And this is really just another one of these, only different because it's bound to get much hotter. Usually these kind are in series with the heaters. Now it's remotely possible that what they've done here is they have these heaters in series right in the wall through these tubes. And this guy, they've used a dropping resistor to feed the correct voltage, which I think was 12 here. Now if I remember, I counted these up, they were all 35. It seemed to me, when I counted them up, including this one, they added right up to 117 or so. So where is that resistor going? So there are two leads coming out of the resistor, but more wires attached to it. So there's a wire coming from the rectifier tube to it, and then going on. So I wish I had the schematic for this, going to this tube. And the other side. So I'm just going to take a guess that this is involved with controlling the heater current in this tube. That's my guess. That's a waste of power. To have extra water go over the falls in Niagara to power this thing, unnecessary. But probably the economic solution for what they're trying to do here. Not sure about that. We really need to look at a schematic. We're spending a lot more time tracing out those wires, but not too interested in doing that. I think I know enough. Keep myself safe, not make a mistake, not return something to somebody and they're going to get a shock off it. Something like that. That would be terrible. Okay, now I will get on. I will replace the capacitors. We'll see how that comes out when I'm done. Why, my gosh, I've talked for half an hour. Oh my gosh. Okay, so I have the three capacitors installed but not soldered yet. And I've removed one of the red wires. I'm going to remove the other red wire. Move here. There we are. Okay, so I have one lead going to this terminal from this capacitor. This capacitor has its positive lead going to this other terminal. This guy's positive lead is going to this yellow wire, and all the grounds or negatives are going to the black wire right here. So, okay, all I got to do is solder that up. Okay, here we go. And I've installed these all right around this big resistor here, which must get worn to some degree. That's probably not the most preferred location for them, so when I've got them soldered up, there's one back here I don't think you can see in the camera. Okay, and the last one is right down there. Yeah, a little tough to get the camera on it. Kind of blocked my own light with the camera here. Oops. Oh, too bad. Yeah, very often the camera, the lights, they all get in my way when I'm doing this kind of stuff. So, there we are. Okay, let's take a look. Let's take a look here. Well, there's a bit of wire hanging out there, but it's soldered in fine. Okay. This one here. Good. The yellow wire. Not a lot of voltage on this wire. But I think I put a 400 volt capacitor in there and it probably won't see 10 volts. And then this one back under here. Good. Now, what about the clearance from the resistor? Well, they're not really, I mean, this is in contact here, but the rest of the capacitors are actually a little ways away. Right underneath them is the rectifier tube socket. That's another source of heat. I think that's going to be just fine. Good. Yeah, not sticking out. Very, very good. Okay. Next step along the way now is to change out these 4 capacitors. We know what this one's doing. We don't know for sure what the others are doing, and without a schematic, I'm not going to take the time to figure out. I will draw your attention to this. If you look at this capacitor here, just a second. See how the end of it is waxed quite nicely. This one's the same. The wax is in there quite nicely. When you look at this one, the wax is popping out. It suggests to me that not necessarily something went wrong here, but it suggests that there's an opening here for moisture to get in. One capacitor that would be of great interest would be the capacitor that conveys the signal from the preamp tube here into the two power tubes, these 2 tubes up here. And they're of interest because their job is to block the B plus that's on this tube from getting onto the grid of the 2 output tubes. These 2 guys are probably it. I mean, what else is there? There's no other capacitors in there. It has to be those. So I'm just going to check by looking at a tube manual and see which pin on these output tubes is the grid. It's just an interest. I'm just interested. Okay, here's my RCA book. 35L6 beam power tube. And what we're interested in is which pin is connected to the first grid. So that would be pin number 6. It says G1, grid 1. You notice there's a screen grid in here also. But G1 is the one I'm interested in. The question is, That's pin number 5. The question is, do those capacitors go to pin number 5 on the two 35L6s? That would be the question. And we will now find the answer. Okay, so we have to count the pins. Here's the key on the tube that I can start counting. We count 1, 2, 3, 4, and 5, and that's exactly where this capacitor is connected, pin 5. There is, yeah, pin 5. And if we come over here, we're going to find the same thing, I think. Let's see. 1, 2, 3, 4, and 5. Oops. A little hard to see. Yep, that's right. So these two capacitors convey the music to the tubes that drive the speaker. On one side of them, they're going to have 120 or 130 volts, and the other side should have 0. Do they really? Maybe we should test this. I've done some work. Maybe now's a good time to test it. You know, the old problem with shotgunning capacitors, which means doing them all at once. You turn the thing on and it doesn't work. Well, I don't want that to happen. So we'll turn it on with these, and I'll take a voltage measurement of what the grid voltage is here to see if there's any leakage, to try to detect any leakage that's going through. Give us a chance also to check the screen voltage, which I did not know which pin it is, but I will in a moment. Yeah, let's do that. Okay, so I'm going to use this meter to measure this effect. Now, this meter is plugged in the wall. That should set off alarm bells. Now, in my shop, when I'm powering up something like this, I've got it plugged into an isolation transformer. Won't go into details about that. So where I want to put the ground connection is on this negative bus point here. Could be some other places that I could use, but I'm going to use this one because I'm certain of it. This is a big ugly clip, so I'm going to use a smaller clip. Clip it on there. Clip this together. There we go. This is the test probe. I'm going to practice a bit. I want to get on pin number I don't remember. Pin number I don't remember. 35L6. I'm going to want to measure a couple of things. I want to measure the B plus on pin 3, and we're going to want to measure the screen voltage, which is on pin 4, and then the grid voltage on pin 5. Expect the grid voltage to show up as 0. The screen and the plate will show up as plus 120 or something of that sort. So it's really 3, 4, and 5. 3, 4, and 5. Pick one of these tubes and identify 3, 4, and 5. Let's take the outside one here. So we're looking for the key. 1, 2, 3, 4, and 5. Okay, we'll practice. It would be, I've already lost it. 3, this white wire. 3, 4, and 5 is the grid. Okay, I think we're ready to go ahead here. Now this is the first time I'm powering this up after putting in these capacitors. If I've made a mistake with these capacitors, it's a big one. It's a big one. So we really want to utilize the dim bulb lights over here. And also, turning this on isn't the easiest thing in the world. I just realized there is no on-off switch except for this. And I don't have the platter on, which means the mechanism will never be driven. The mechanism gets its drive from the spinning platter and a gearing arrangement in here, but no platter, no drive. So this will turn, this won't move. That's perfect. You can switch this on. So there's no power being supplied, so I'm going to put this on, but not... Am I going the wrong way? it's on. So what should happen, I'm going to throw the switch. This motor should start turning, the wheel should start going around here. A few minutes later, this thing will warm up. I don't have a speaker hooked up. You just realized. Okay, we'll hook up a speaker. Okay, speaker connection is here. And here. Okay, so I have a shop speaker connected. The meter is set to 150 volts. 150 volts is full screen, or full deflection. And let me get the solder out of here. Okay, I think we're ready. So what I expect to see when I turn this on is these lights will come on a little bit bright, but then dull down pretty quick. There we go. There they go. They're dulling down. It looks very different in the camera than with my eyes. So you see it dulling down. That's good. Okay, nothing exploded. That's also good. And the supply voltage is very low at 88. Just going to give it a moment here. You can see the wheel is turning on the record player. See how quiet that is? Can't hear a thing. So it's going down as the tubes begin to conduct. So we're going to apply full voltage. Now we can hear the motor. That's another thing I wanted to investigate, is the source of the sound. Let's do that right now. If I pull this off, you can still hear sound. It's just the motor spinning on its own. Okay, ignore all that. First thing we're going to check is a B+ level. Watching on the meter now. I'm going to go on the positive lead of one of those big capacitors I installed. There we go. So on the 150 volt scale, that meter is saying 110. And we'll go on the other one here. It's saying 100 and I think the last one was 100 and this one's 110. Yeah, 100 and the other one was 110. So 110 is the highest voltage available. We'll come over here and we'll look on the plate now. This is the white wire. Just under 110. Not a lot of B+, but now what are we? We're running at 112 volts. That's just a little low. I'm not sure why it's that low. Let me just put it up a little wee bit. Okay, so it's at 117 now. Okay, we'll check the B+. 100 volts. Not a lot. Now we'll check the screen voltage, mainly to make sure it's there. Yep. Now we're going to check the, well, rather than check the grid voltage, we can check the drop across the cathode resistor by looking at the voltage that's on the bypass capacitor. There, get back down here again. So here's the bypass capacitor. The voltage there is going to read positive, but it's going to be very low. Let's check here first. Ooh, that's not low. Okay, that's unexpected, completely unexpected. Okay, so I'm thinking we better just stop for a minute because that's really not at all what I expected. Not at all. See, it'd be a little helpful if I had a schematic here. Well, let's see where I hooked it up to this yellow wire. Let's see, on the capacitor here it says 40, 40, 20, and then it says 150, 150, 150. So even the 20 is a 150 volt capacitor. Let's see where that yellow wire goes, because it's just disappearing from view, and I made an assumption. And you know what happens when you make assumptions, which I was trying to avoid so much this morning. Okay, now let's remove the ground connection here for the meter. The yellow wire comes along. Very tricky to see. I don't think you're going to see it in the camera. It's just buried right at the bottom of everything in here. Okay, I think I see the connection point. Yeah, I do. It's connected to a grid. This doesn't make any sense at all. It's not making any sense. Not any sense being made. Is there another yellow wire in there? The signal grid. When I said the grid, the signal grid is what I was talking about. I'm sure I'm seeing it there. It's just buried under all kinds of wires and parts. Well, that would indicate, if that's really true, that would indicate one of these capacitors is shorted right out. Or I've totally misinterpreted what's going on here with these capacitors. So an interesting question is, how are these two output tubes being operated? They could be in parallel, or they could be in a push-pull type arrangement, which is what I was guessing. And then the 12AX7 is not only a preamp, it's also providing an inverted signal for one of the tubes to make the push-pull thing operate. Power's off now. Let's look at that transformer again. So I can see 3 wires here coming in one side and 2 going out the other. So that center tapped output transformer indicates these are in push-pull arrangement. Yeah, certainly I've lost it here. I cannot account for what I'm seeing. Oh, wait a minute. Wait a minute here. Okay, that yellow wire is not connected to the grid. It's connected to the next pin over. It's just confused. Okay, the next pin over on where's my tube manual? Where'd it go? Here it is. 35 L6. So we have pin 5 is a grid, pin 6. Pin 6 is not listed here. Pin 6 is a freebie. Is that really pin 6? If we count backwards, let's count forwards. 1, 2, 3, 4, 5. It's on pin 6, and you know what? There's no 2 pin in there either. So pin 6 is a freebie, it's a connection point. Doesn't explain why we're getting such a high voltage back here. I'm not getting something. Let's look at pin 6 on the other tube. It should be basically the same arrangement. Pin 6 on the other tube is completely unconnected to anything. You can't really see it there in the camera. It's just an empty pin spot, and the terminal has never had a wire connected to it. So they're just using this as a connection point. Well, it's possible that this is not a bypass capacitor, it's a further filter capacitor. And I don't quite get it. That would mean this could have no bypass capacitor. That's possible. Let's look at the cathode here. Cathode is pin number 8. Pin number 8. Okay, so pin number 8 is the last pin in an 8-pin tube. So that's pin 8. And it's connected to this pin on the other tube, which is also pin 8. So the two pin 8s are connected together. Two cathodes connected together. That's the cathode resistor. Now, is there a capacitor across it? I don't think there is. So what exactly this other one's doing, good thing I didn't put in a 25 volt capacitor here. It's doing some more filtering. Maybe doing some filtering related to the preamp tube. I don't know. Well, that's a total surprise. So that's a 400 volt capacitor, so I don't have to worry about it in terms of the voltage on it. Why did I do that? Keep it there. Yeah, okay, I'm a little beside myself. Well, then what I thought I was measuring, I was not. What I want to measure is the voltage here on the cathodes. That's where I want to go. Okay, let's reconnect the meter. This would be easier with a schematic. Where'd my meter go? There it is. Reconnect the ground connection. Okay. Everything's the way it was. The meter's at the ready. Okay, we'll put the power back on. Just shoot it through the dim bulbs, just in case. There goes the motor. Here we are, full voltage. You can see it on this meter here. It's not accurate though. Give it a moment. Okay, so the plan is to, let's start again. Let's start with that high voltage I read on that capacitor there. There it is again. 100 volts. Now we're going to read over here, cathode, expecting something like 5 or 10 volts there. This is the 15 volt scale on my meter now. So 15 volts full scale. 8. 8 is the number. We'll see what Mr. RCA manual says about that. Typical operation. Cathode bias. It may not actually give it. It may give a cathode bias resistor value 180. It doesn't actually give you the volt drop on it. 180, what's in there is a way off from that. I think that was the 82. They're suggesting 180. But there's a plate voltage involved. Plate supply is 200, but let's see the plate supply. Well, let's look at this one. That's for fixed bias. Fixed bias, it's a different way of doing it. With fixed bias, You're looking for minus 7 volts, 7.5 volts with 110 by 110 on the plate. So, you know, we're roughly there. I don't think there's any problem. Now we're going to try to read the grid voltage. The idea is to see if these capacitors are leaking. So if they leak, there'll be a positive voltage there. Otherwise, it should say 0. There we go. You can see the meter going up. So that's 4.5 volts on that one. And what about the other one? The other one's a little hidden here. And it's got about, what would that be? That's about 1 volt. So you got 1 volt on one of them, 4 on the other. That's not good. So that suggests, because on this end, the other end of the capacitor, let's check this out. See if I'm lying. The other end of the capacitor should have like the 110 volts on it. It's got 70 volts, okay. So you see the high voltage on one end of the capacitor. The idea of the capacitor is to block this. Oh my god, I didn't have the camera down there. I'll just repeat that. So you can follow along. So I was reading this end to see the grid voltage, little volts, 4 volts and 1 volt. Now I'm reading the other end of this capacitor. That's 70 volts and 70 volts. Okay, power off. What we'll do now is I'll change these two capacitors, grid blocking capacitors, and then we'll repeat these measurements. See what's up. Okay, I thought this would be two videos would do it. Looks like it's going to be 3 videos. So I don't think I'm going to get to the meetings of this today. So it's a 0.1. This capacitor is the one that led to a 1 volt. 1 volt on the grid. This is the one that led to 4 volts on the grid. Seem to be in very good shape. But that doesn't mean much. Let's take it over to the tester and we'll find out the truth. Let the truth be known. What this is going to do, this device is going to put some voltage on these capacitors, DC voltage, and then measure, or respond rather, to any current that leaks through it. It's a very sensitive instrument. Small leak should be quite apparent. Okay, so a little bit of a challenge in the camera to see, but down here is an opening in the eye. It looks like a pie down here. I'm going to put 50 volts across this capacitor, and when I hit the switch, during the charging the eye will snap closed and then it will open up again. If it opens up like that, no leakage. So it's opened about 2/3 of the way. A good capacitor would open right up like that. Now we're going to put 150 volts on it, and I'm sure it won't open. This one was the 4. So let's go back to the 50 volt test and watch. Look very carefully at how the eye responds. Maybe I can make this a little better if I close this door. No. Maybe if I shine this light elsewhere. No. Maybe if I turn this one off. Yeah, a little tough to make that eye a little more apparent without doing a lot in here. Okay, so I'll keep an eye on it. Here we go. This is 50 volts on the first capacitor. Same as last time, about 2/3 of the way. This is supposedly this would be the leakier of the two, because there are 4 volts showing up on the other side of it. So now we'll put on this one. Do the very same test. See what it shows. So this one opens up almost all the way at 50 volts, at 150. It's trying. It's not going to open up though. clearly, you know, you couldn't see it in the eye, but I could. Clearly there's a difference between those two capacitors, and it adds up. The apparently leakier one leaks more. Okay, I'm going to put in a couple of new capacitors there. I'm going to use this type of capacitor. This is a bit of overkill. It's the right size, but the voltage on this is 250 volts, which is oversized, but that's okay. I'm going to put those in, and then we will repeat the test. Okay, those two capacitors are in. I noticed that, of course, now that I've disconnected the wires to this thing, it's just as floppy as can be. So I am going to do what the installer should have done. I'm not going to take it out. I'm just going to twist the locking tab here. There's another one over here. They're solid as can be now. So somebody forgot to do that. Now, the two capacitors in here, soldered in, they're not sticking out. We're ready to repeat the test. Put the voltmeter back on. The idea now is we should read 0 volts on the voltmeter on the grids under this test. Now, I did this just the other day with a radio, and to my surprise, one of them still had a bit of a voltage on it. I have no idea how that happened. It's still bothering me a little bit. Yeah, the ground connected, the speaker connected. Everything looks okay. A lot of junk on my bench here, which I don't like, but we're going to go ahead anyway. Okay, everything's safe. Power on. Go, full power. Give it a moment here. So these capacitors, if they leak, can leak charge kind of slowly, and it takes a little while for the grid voltage to go off, and the result of that can be a quieting of the tube. So you have something like this, you turn it on, the volume's good, but then over a little bit of time the volume drifts away. It could be grid blocking resistors that are doing it. Okay, the voltage we're on over here is 150, that's a little high. Put it on 15, and remember we got 4 and 1 volts. So this one said 4 volts, what do we got now? Nothing showing up, and this one was 1 volt with nothing showing up. So now we're at 1.5 volts full scale. So this is a very sensitive reading. It's just moving the needle at the tiniest amount. That's not a problem. And this one is exactly the same. Tiniest amount. Not a problem. Okay, so the problem with the way things were with those old capacitors is it's throwing the bias off on the two output tubes. And that's going to have a couple of different effects. Depends upon how bad it is. It can be everything from you'll never know to badly distorted to silence. All those things are possible. And if you don't have the right bias, the tubes conduct too much current and it wears them out fast. So that's why it's so important to do that. Now what we're left with now are two uninteresting capacitors over here. One of them we already talked about. Actually, it is interesting, but we've talked about it. And then we got these two over here. And I think I'm just going to go ahead and change all those out. And then we're going to really give this guy a good test after that. And it looks to me like I thought this would be 2 videos. Did I already say that? It looks like it's going to be 3 videos. Okay, that's great. I think I said there's nothing interesting about these, but maybe there is something a little bit interesting here. This capacitor, I lifted up this resistor to get it out of the way, and I could see that there's a lot of darkened wax here, and the end cap of the resistor capacitor has popped out. What's going on here is this guy's being heated up by this resistor, and it's caused the wax to flow and degraded this capacitor. Now this is the one that goes between the chassis and the B-. So this is a capacitor, you do not want this thing to short out, or you get that safety issue happening. Which, so is it shorted? I doubt it very much. Is it still what it's supposed to be? I doubt that very much too. Does it leak a bit? Yeah, I would think so, yeah. A little bit of a leak, give you a little bigger shock. Okay, I've cut the leads free, so let's take it out. Now you can see how the end of it has kind of popped out. And this wax has either come off the outside surface or it's come just around the, I don't know, who knows where it's come from. Let's put this guy right to the test though. Right away. I didn't think I'd be doing any more video on this, but because this guy is important in terms of keeping you from getting a shock, it's worth investigating. And I don't like making assumptions as much as I can avoid it. I'm often surprised by these tests. I usually develop a hypothesis and take a guess. My guess is this one will show up leakier than the other two. You're having a little bit of trouble seeing the eye. I just can't make it more visible, really. Here we go, 50 volts. What do you say, capacitor? Open right up. It's really not so visible here. No, I can't improve it. Here we go. 150 volts. So it's actually better than the other two. It's surprising to me. But leaky. Because a brand new capacitor, you could crank this up to 450 volts and that eye would pop right open wide. Not with these old guys. Okay, that's the story there. Okay, let's give the last two capacitors a check. The last two I took out of the tone and volume control box. Okay, you can see the eye a little better here. I realize I need to increase the amount of light in my shop for that to work. Here we go. Open right up, 150. So this is the best of the bunch, but I mean, you can't expect these to be perfect. What would be interesting is if I could go back in time and grab one of these right out of the factory and do this test with it. But I suspect it would test perfectly. Okay, last one, 50 volts, right open. So these two might be a little better. That's right open at 150. These might be a little better because they were in that other chassis away from the heat. Just maybe. Maybe that saved them. So here we are. So I've got new capacitors in here. All the old guys are gone from in there. Making sure I soldered everything. Good. Ready for a test. So what exactly am I testing here? I do have the cartridge plugged in. Guess we could be testing for sound to come out of the speaker if I rough up the here it is. Just to hook up the speaker. If I rough up the cartridge a little bit with my finger, and that's going to be it. So, speaker connected. We're all set. Okay. Eyes on the lights. Ready? Oh, we don't have it plugged in. Ready? Again. Ooh, what was that sound? I think it's just the motor turning. Okay, full power. Well, I didn't do anything. I just spoke full power, and I guess the motor must have heard me. Here we go. Now we're going to give it a little bit of time to warm up and entirely. And then I am going to rough up this guy here. I guess we need the volume turned up too. Step back a little bit. That's all we need to do. There's no needle on there. Good. Hum. There's bound to be a tiny amount of hum with these amplifiers, but it's not like it was. Very good. Okay, so tomorrow it's all about the record player and getting everything back together. Let me turn this off before I forget. And a little hard to forget that's running. And we'll take it from there. Tomorrow should be finished. Great. Thanks a lot for watching. Hope you got a kick out of that and maybe learn something along the way. See ya.